Welcome to Basics of Building Science, a WISE educational program brought to you by Console. This course is a WISE educational program brought to you by the California Energy Commission's EPIC program. At the end of this course, you will be able to define energy and the first two laws of thermodynamics, cite the types of heat flow, understand the relationship between thermal and pressure boundary, calculate heat loss over time, understand the concept of the house as a system, and anticipate problems when the house as a system concepts are not used. Let's start by talking about energy basics. What is energy? It is a measurable quantity of heat, work, or light. Energy can be put into many different categories, such as chemical, nuclear, magnetic, sound, and elastic. While energy comes in many different forms, it generally qualifies as one of two types, potential or kinetic. Potential energy is stored energy, like that in a cord of wood. Kinetic energy is transitional, like when that cord of wood starts to burn. Through a chemical reaction, the potential energy in the wood changes into kinetic energy in the form of heat and light. Two of the most basic principles in the study of building science are the first two laws of thermodynamics. These laws are fundamental to understanding how energy behaves. The first law of thermodynamics is an expression of the principle of conservation of energy. It states that energy can be transformed, but cannot be created or destroyed. Stated simply, energy is neither created nor destroyed, it simply moves about from place to place and changes form. The second law of thermodynamics describes how thermal systems naturally seek equilibrium, and that there is only a finite amount of work that can be done with the specific energy level of a given system. This law states that heat will always move from the hotter area to the cooler area. The rate of that transfer will be based on the difference in the temperature. Heat cannot flow from cooler areas to hotter areas without adding additional energy to the system. In building science, we use the British Thermal Unit, or BTU, to measure thermal power and thermal energy. 1 BTU equates to the amount of energy needed to raise 1 pound of water 1 degree Fahrenheit. That is the approximate amount of energy produced by 1 lit wooden matchstick. Now let's move to heat transfer. There are three basic mechanisms for heat transport: conduction, convection, and radiation. Conduction is the transport of heat from molecule to molecule through direct contact. This is the type of heat transfer occurring when a pot is heating on an electric stovetop. It is a very predictable type of heat flow and is a type of heat transfer that we are trying to reduce when we insulate a wall or pipe. Convection is a transfer of heat energy within a moving fluid like water or air. Hot fluids are less dense and rise. Cooler fluids are denser and sink. This creates convective flows that transfer heat. Heat radiates from a heat body in the same way that light energy radiates from a light source. The energy radiates in all directions equally, and heat moves from one body to another, as long as they have line of sight communication. The heat does not need a medium through which to travel, as in conduction and convection. The energy will pass through space or through any clear medium that is not opaque to radiant transmittance. Radiant heat is the heat that you feel from a fire on a cold day. Standing away from the fire, you are not touching the fire, so there is no conduction. The heated air is rising above the fire. The air around is still cold, but that warmth that emanates from the fire is radiant heat. There are two boundaries that play a role in separating the indoors from the outdoors. The thermal boundary prevents heat flow between the inside and outside of the home and is typically where the insulation is placed. The pressure boundary prevents airflow between the inside and outside of the home and is usually the interior drywall. While the pressure boundary is usually the drywall, that is not always the case and can be much harder to identify than the thermal boundary. To achieve the most efficient envelope, these two boundaries must be fully aligned, continuous, and in contact with each other. Gaps in these boundaries will allow heat to more easily transfer into and out of the home. The envelope of a home will be constructed of materials that will conduct heat. How quickly or slowly that heat can transfer through the material is measured as its R value. A higher number indicates that the material has more resistance to the transfer of heat. If there are several different layers, you can add the R values of the materials to determine the overall R value of the assembly. The rated R value can only be achieved if the material is installed per the manufacturer's specifications. Where R value measures the resistance, the U factor measures the transmittance or conductance of the material. The U factor operates in the opposite manner from the R value. With the U factor, the lower the number, the slower the heat transfer, and you cannot add the U factors together to get the total for the assembly. You can convert U factor to R value and vice versa. To find the R value, you will divide 1 by the U factor, and to find the U factor, you will divide 1 by the R value. In addition to the three means of heat flow discussed earlier, conduction, convection, and radiation, heat flow in a home is also affected by infiltration and exfiltration. Infiltration is the uncontrolled movement of air into the home, where exfiltration is the uncontrolled movement of air out of the home. These are not to be confused with ventilation, which is the controlled movement of air into or out of the home. Infiltration, exfiltration, and ventilation are all measured in cubic feet per minute, or CFM. For each cubic foot of air that enters the home, 1 cubic foot of air must leave the home as air pressures equalize. Just like the second law of thermodynamics, air pressure also seeks equilibrium. Areas of high pressure will move towards areas of low pressure. In order to have air movement through a surface, you must have three things: a hole, a pressure difference, and a volume of air. When all three are present, the volume of air will move through the hole until the pressure difference is no longer present. Stack effect is caused by convection and air exchange working together. Warm air in the home will rise to the ceiling, creating a positive pressure, allowing it to pass through the holes and escape to the outside. This loss of warm air at the ceiling creates a negative pressure at the ground floor, which draws in cold air from the outside. A continuous air barrier will greatly reduce this process. Wind blowing across a home will create pressure differentials on either side of the home. These pressure differences will drive air into and out of the home. Just like the stack effect, the wind effect can be greatly reduced with a continuous air barrier. The mechanical effect is caused by equipment in the home that exhausts to the outside. While this does cause outside air to move into the house, it is not considered infiltration because the amount of air movement is controlled by the fan exhausting the air. Proper location of mechanical equipment and installation of balanced ventilation systems will greatly reduce the amount of outside air that is pulled into the home. This exchange of air cannot be completely eliminated, as it is needed to maintain acceptable levels of indoor air quality. Every home needs to have a minimum number of air changes per hour to rid the home of harmful contaminants and provide fresh air for the occupants. And finally, let's talk about the house as a system methodology. A house, with all of its interacting and interdependent components, is the exact definition of a system. A system has structure. It contains parts or components that are directly or indirectly related to each other. A system has behavior. It contains processes that transform inputs into outputs. And a system has interconnectivity. The parts and processes are connected by structural and/or behavioral relationships. A house consists of many interdependent parts. The operations of one of those parts will have a direct effect on the other dependent parts. When all parts are working as they should, you will have a comfortable, safe, efficient, and durable home. When one of those parts experiences an issue, the others will also experience problems. The primary components of the house are building envelope, space conditioning equipment, lighting and appliances, mechanical ventilation, water heating and distribution, and the occupants. While the occupants are not a physical part of the house like the others, the behaviors of those living in the house directly affect how those other systems perform. If those systems cannot handle the loads put on the house by the occupants, then it will become an unsafe or inefficient house. For example, an attic without insulation will make the heating and cooling system work harder than necessary. This will decrease the HVAC equipment's life and will result in higher than necessary energy bills. Leaky recessed lighting fixtures will increase heat loss and heat gain as air can freely move from conditioned to unconditioned space. Mechanical ventilation that does not exhaust to the outside of the house will allow moisture to condense on the underside of the roof, causing it to rot over time. Any modification to one of the components will have either a positive or negative effect. Always consider what effect any change may have on the other components of the house. We have prepared 4 examples of what can happen when one component is modified without consideration to the other components. Let's take a look at them one at a time. Insulating and venting an attic without air sealing could cause moisture damage on the roof. In the wintertime, warm, moist air will rise through holes in the ceiling and find their way into the cold attic. The warm, moist air will then condense on the cold roof deck, leading to a rotten roof. Air sealing without insulating could cause mold and moisture damage. In the summertime, uninsulated wall cavities will be warmed by the heat transfer from outside and will then come into contact with the cool interior drywall. This will allow the moisture to condense and create an environment where mold will grow. The opposite can happen during winter months where warm air condenses on the cold outside surfaces. Air sealing and insulating without attention to the HVAC system will not reduce energy lost through a poorly sealed duct system. Getting the heated or cooled air where it needs to go is just as important as improvements made to the thermal and pressure boundaries. Air sealing without combustion safety testing can potentially kill someone. Combustion appliances that vent to the outside need a constant supply of air to work properly. Reducing that supply by air sealing can create a situation where the appliance will backdraft, polluting the indoor air with carbon monoxide. Combustion safety testing is very important to the health and safety of the occupants. Carbon monoxide is a colorless, odorless, tasteless gas that is highly toxic. It finds its way into homes through poorly vented combustion appliances that suffer from incomplete combustion. Carbon monoxide poisoning can range from headaches from minor exposure to death from high exposure. Long periods of minor exposure can lead to serious health issues in time. Carbon monoxide detectors can be installed to alert occupants of a potential issue. For more information on building science principles, be sure to check out Residential Energy by John Krieger and Chris Dorsey. This has been Basics of Building Science, a WISE educational program brought to you by the California Energy Commission's Electric Program Investment Charge Program. For more information, please use the contact information on the screen.